In this video, we're going to wrap up the topic of descriptive statistics by covering a few vocabulary terms. First, each of the descriptive statistics that we've covered can be calculated with data from an entire population or with data from a sample. A descriptive statistic that's calculated with data from an entire population is called a population parameter, and a descriptive statistic that's calculated with data from a sample is called a sample statistic. So the mean of a population, the median of a population, or the standard deviation of a population would all be called population parameters. The mean of a sample, the median of a sample, or the standard deviation of a sample would all be called sample statistics. Population parameter and sample statistic really just mean population statistic and sample statistic. It just happens to be that people in the field of statistics have decided to use the word parameter to describe the population statistic. Here are a few examples of population parameters and sample statistics. The mean age of all people in the Bay Area would be a population parameter. The median GPA of all college students in the US would be a population parameter. And the standard deviation of heights of all people in San Jose would be a population parameter. Notice how these are all statistics that tell you something about an entire population. The mean age of 50 selected Bay Area residents would be a sample statistic because it's the mean of a sample. And the median GPA of 100 selected US college students would be a sample statistic because it's a statistic based on a sample. So remember, a population parameter is a population statistic, and a sample statistic is just a sample statistic. Usually people can't calculate population parameters. To calculate a population parameter, you have to have data from an entire population. Researchers are typically interested in population parameters, but they can't calculate them because they don't have enough data. Since people can't calculate population parameters, they do the next best thing. They collect data from a sample, and then they calculate a sample statistic to estimate the population parameter that they're interested in. Whenever you calculate a sample statistic to estimate a population parameter, the sample statistic is likely to be at least somewhat different than the population parameter. In other words, the sample statistic is likely to be at least a little bit off target. That's because basically no sample is perfectly accurate. Whenever a sample statistic is calculated to estimate a population parameter, the difference between the sample statistic and the population parameter it's estimating is called sampling error. Sampling error is just the amount that a sample statistic is off target. So here's a diagram of the concept of sampling error. We have a population mean that we're interested in, that we would like to know, and we have a sample mean that we're calculating to estimate the population mean. The difference between the sample mean that we've calculated and the population mean that we're interested in is our sampling error. Here's an example. Imagine I want to know the mean income of the entire Bay Area. That's a population mean I'd like to estimate. To estimate that population mean, I randomly select 200 people in the Bay Area, I record their incomes, and I calculate the mean income of my sample. The answer is my sample mean. The distance, or the difference between the sample mean I've calculated and the population mean I would like to know is my sampling error. If the mean income of the Bay Area is 40,000 and my sample mean is 30,000, then my sampling error is 10,000. I'm off target by $10,000. So sampling error can't be avoided. It's just a consequence of using a sample to estimate something about a population. But the goal is to minimize sampling error. The goal is to select a sample that's as accurate as it can possibly be. And there's actually two factors that lead to less sampling error. One is a larger sample size. When you randomly select a sample from a population, you're likely to get a more accurate sample if you use a bigger sample size. For example, a random sample of 1,000 people is likely to be more accurate than a random sample of 10 people. So a larger sample size makes it likely that you'll have less sampling error. Second, sampling error is typically less when there's less dispersion in the population, or more similarity between population members. When the population members are more similar to each other, you're likely to have a more accurate result and less error. When the population members are widely different from each other and vary a lot, you're likely to have more error and a less accurate result. Here's a quick example. Imagine I wanted to estimate the mean age of the 5th grade population. I'll probably get a pretty accurate result with a random sample of even 5 5th graders. If I record the ages of 5 5th graders and calculate the mean of the age of the 5 people, that sample mean is going to be pretty close to the population mean. That's because 5th graders are basically almost always the same age. There's little room for error. However, if I recorded the ages of 5 randomly selected people in Pleasant Hill, I'm likely to get a much less accurate result because my sample of 5 people could easily end up with a few younger people or a few older people that would throw off the mean of my sample. So overall, you're likely to have less sampling error with a larger sample size and with less dispersion in the population. Now, the amount of dispersion in the population isn't something that you can control. It just is what it is. So if you know that the population that you're sampling from has a lot of dispersion, then what you have to do is use a larger sample size to make up for it and to make it likely that you'll get a more accurate result.